Hey there, Spiceheads. Thanks for hanging out with us for today's webinar, Powering Your Dream Server Room, Part 2, brought to you by Cisco and Eaton. Before we get started, I do want to remind everyone this webinar is being recorded. If you have to step away for any reason, you will get an email with a link to the webinar in just a few days. Also, there's a Q&A box on your screen to the left, and I encourage you to submit your questions at any time during the presentation. If we're not able to get to your question live, someone will be able to follow up with you. As usual, we also have a live chat, so join in by clicking on the widget at the bottom of your screen. Now let's get started. Today's presenters are Tony Harvey, Cisco Senior Product Manager. Tony has been with Cisco for 7 years, and he used to rebuild and ride motorcycles. We also have Jeff Shearst, Applications Engineer for Eaton. He's been with Eaton for 4 years. He's an Operation Iraqi Freedom vet, and he won his local Rec League Slam Dunk competition. So congratulations on that, Jeff. Now let's get started, guys. So let's start this off with a question. What sets Cisco HyperFlex apart from other hyperconverged appliances?
All right, so I'll take this one as I'm from Cisco and Jeff's from Eaton. I'm sure you'd be more entertained if Jeff tried to answer it, but I won't make him do that today. And for those of you that were on the last presentation, I promised not to say power calculator too often this time, although I know that those of you that are planning to drink to this, that may be a bit of a disappointment. I will say single pane of glass several times though. So what is the difference in Cisco HyperFlex? There's some real innovation there. So things like integrated management and data services, independent scaling of compute and capacity, dynamic data distribution, and continuous data optimization. Those are really the 4 areas that we'll be looking at as competitive differentiation. And what I'll do is I'll take each one of those in detail. So the first thing is that we built with HyperFlex, with our partner SpringPath, a scale-out and distributed file system that was built from the ground up to work in a hyperconverged environment. In fact, the founders of SpringPath actually came from VMware, and they were looking at scale-out file systems as part of their work at VMware. And they wanted to develop this new file system to really work well in that scale-out environment. So one of the things that they wanted to do was have a simple system that scaled very, very easily. So you could start with as few as 3 nodes, and you just need that for data protection and replication. Then as you add more nodes, as you add more servers, rather than you having to manually redistribute the data or the system having to redistribute the data based on the locality of a particular VM, they just wanted to treat every server the same, so that as a new server gets added in, the data just gets redistributed across all of the servers in the array. Think of this as an almost a RAID array of servers. The data is distributed across all of the servers. The VMs that are running on that server simply go and get the piece of data from the appropriate server when it's needed. And that removes any data locality problems. So if you vMotion a VM from server 1 to server 2, it doesn't make any difference to the performance of that VM because all of its data is distributed anyway. And then you keep on adding servers, you scale compute, you scale storage, you scale performance, and you scale capacity all at the same time, with that rebalancing happening completely automatically. And then, if you need to retire an older server, you simply tell the system to retire that server. It rebalances the data on the existing servers, and then if you want to add an updated server in, you again migrate the data back. And all of that process is completely automatic and you can reschedule it so it's not happening in background during your heavy business hours. You know, it's happening at 2 a.m. or whenever is a good time for your business for that to happen. So that's what we're doing. And internally what we do is we have a hook essentially into VMware. It's called IOVisor, and what that does is it using a standard VMware method, it connects into the hypervisor, takes over all the storage attached to the drive, to the system, so that the controller VM has direct access to the drives. We also add this VAAI plugin that offloads snapshots and clone operations, and what that means is that all your snapshot and clone operations actually take place. And in fact, all of your management operations pretty much take place from the standard vCenter environment. Currently, we only support vCenter, but things like Hyper-V and other operating system are in plan, and they're being worked on right now. And then the IO Visor module presents NFS to ESX and then figures out where all the IO is going to go to. Be it a read IO, where does that data come from, or a write IO, where does that actually get laid out to maintain redundancy and reliability and performance. Underlying all of this is a unique architecture that was built from the ground up for hyperconvergence. The actual official name of the file system, it's called a distributed log structured file systems. Log structured file systems, try saying that 3 times really quickly, are actually a file system that's been written about in the computer science for quite some time. But where they've really started to come out now is in the way that they use the data structures on the disk. One of the things that you're always trying to do with a log-structured file system is to build very large blocks, or relatively speaking, large blocks of data in memory, so you can do, relatively speaking, again, large sequential writes to disks. The original purpose behind this was to try and get around the random read problem that you would see on a spinning media disk. A typical 15K RPM hard disk drive was pretty damn good at writing data sequentially, but when you had to get to random reads or random writes and you're moving the disk head about a lot, that's when the performance started to go down. So log-structured file systems tried to turn everything into a sequential write and do all of the reads from the cache, because in that kind of environment, if you have enough memory and you have enough fast storage, then you can do the majority of reads from cache, and then all of your writes can be written out sequentially to get good performance. Now, it so happens, although log-structured file systems were designed some considerable time ago, that works really nicely with Flash, because one of the things with Flash is you don't want to do a lot of small random writes to a Flash disk, because that doesn't work well with Flash technology. This is not a Flash technology presentation. I'm sure you can find more things about that on Spiceworks, but one of the things that doesn't work well for Flash is small random writes, because of the nature of the way that data is written to Flash and the fact that you may have to erase a block before you can write a block. Writing large sequential blocks to Flash actually helps with the endurance of Flash. So that log structured file system works really well for Flash, and of course you can use a Flash disk as your cache to improve the performance of reads, so again that works really nicely with a Flash environment. So that's what we get from that log-structured file system. It's a modern file system that works really well for a Flash design, a system based around Flash. On top of that, we can do things like advanced data services, those snapshots and clones, and then the data optimization with inline and dedupe and compression that really you don't have to trade off anything to get those. You're not losing any performance because of that inline dedupe and compression. We've tried turning it off. In the system you can't do it, but we can internally. And actually what it does is it really doesn't give you that much better performance. There's no real performance difference. And as I already mentioned, the Flash endurance and disk performance. Integrated compute, storage, networking, and hypervisor all integrated together and all managed through that single pane of glass vCenter. And this helps eliminate a lot of those management silos where you have a storage manager, you have a network manager, you have a server manager. All of those are brought together in the HyperFlex environment so you can manage them all from a single location. Already mentioned the independent scaling of compute and capacity. This is one of the things I talked about last time, but it is a very important feature for the HyperFlex data platform. You can scale capacity within the nodes by adding more servers with storage attached, or if you've got plenty of storage capacity and you just want to add some compute, we can add non-HyperFlex hosts just with IOVisor running in a VM on those hosts just for compute capacity. And the way we do this at the moment is through our blade architecture. Both systems are connected to the same set of fabric interconnects, and that's one of the other important competitive differentiators for HyperFlex is that we take care of the networking for you. There's no having to go to your networking guy or lady and get them to set up multicast for you, because that is all taken care of within the fabric interconnects, and we manage all of that for you. And then you can just keep more adding and scaling compute without scaling the HyperFlex or without having to scale capacity. Again, start Hyperconverged rack servers, compute and storage capacity, and then add in some blades. You can even connect the existing blades for compute, just make them part of the HyperFlex solution. And then you can add Hyperconverged rack servers. And over time, you'll be able to grow this solution beyond the, at the moment, 8-node cluster. You'll be able to grow that beyond an 8-node cluster, up to 16 nodes. And again, all of that is within plan in our roadmap. Key things about dynamic data distribution. If you build on a conventional file system, so if you take the existing Linux, I can't remember what it's called now, the existing Linux file system, and then build that into a hyperconverged solution, then one of the things that you're going to run into is that conventional file systems were never designed for distributed data and scale out. So typically what you'll see is that systems will write locally and then replicate. So if you start getting a very busy VM, you can actually start to see performance hotspots. With the HX data platform, we stripe data across all of those nodes simultaneously. All of that striping is done by the IOVisor plugin, managing that across all of the nodes in the system automatically. So we leverage the cache across all SSDs for fast writes. Every single platform or server platform in the HX environment has an SSD. We use that for cache. It gives us balanced space utilization, so no data migration is required following a VM migration. One of the things that you will see in some other environments is that when you do a VM migration, there'll be a sudden burst of traffic from the system because it needs to re-replicate the data to where that VM has landed. With HyperFlex, that never happens because the data is automatically all distributed all the time. And that gives us very efficient capacity and network utilization. We can control the network utilization because all servers are being written to and read from all of the time. And we can distribute all of the VMs across all of the servers. And that gives us balanced space utilization as well, where, if we have one VM with a large data store, again, that's distributed across all of the servers. If we have another VM with a medium size, again, it's distributed. And if we have another VM with a smaller size data store, again, that's distributed automatically. And then if we move VMs around, we don't need to do any data migration. Just move the VM from server 3 to server 1, and the VM can access its data no matter where it is in the environment. High resiliency and very fast recovery. The platform can sustain up to 2 simultaneous node failures without data loss. That replication factor is tunable. If you want to take it down to just one platform without data loss, then that's not a problem. You can take multiple drive failures within the system, multiple drives within one server, multiple drives where you're talking about drives across multiple servers. All of those faults can be dealt with very, very easily. If a complete node fails, you just move the evacuated VMs, reattach them, no data movement required. You can then rebalance without that, or you can just move to bring in a new node and rebalance across all of the systems automatically. You also get out of that non-disruptive operations. So you have this file, VMDK, that's being distributed across all of my servers. As you can see, I write that file across all of my servers. I then replicate one or two additional copies to the other servers based on my replication factor and the level of fault tolerance that I actually want to deal with. And then that becomes my data store. I lose a server, no problem. My VMs can get my data from wherever they need to go. Move them around, no problem. VMs can get my data from wherever it needs to get begotten from. And we can handle multiple disk failures. One of the things that we can do within that is we can actually re-replicate the data. If you do lose a server, we can re-replicate the data to restore back to the original number of copies, so you have a cluster that comes over time will come back to being fully fault tolerant. And then when you repair that, again, the data gets redistributed back and becomes rebalanced. Sorry, I'm waiting for the builds to flow through. Rebalance those VMs and remove the data back so that my system becomes completely stable, get all of my capacity back. One of the things that allows you to do is, for example, rolling software upgrades. You can upgrade server 1, take it out of production, let the system rebalance, upgrade server 1, let it roll out again. Upgrade server 2, upgrade server 3. So you can do rolling server upgrades very, very easily in this environment. We also provide continuous data optimization, whereas part of the way that we work with a log-structured file system, because we collect data in cache prior to writing it out to the disk, we can do inline dedupe and inline compression without requiring special hardware or any performance impact. And that's part of the nature of the log-structured file system. It allows us to do that as part of that data collection process before we write it all out to disk. It's all integrated management and data services. We have all of the hardware setup is done through UCS Manager, which is familiar to well over 50,000 customers worldwide. There's an awful lot of UCS out there. All the server and the network settings are in pre-configured service profiles, so everything is done for you. All you have to do is assign those service profiles to individual servers and then bring those servers up, and they will come up with the correct configuration, the correct network configuration for working. Instant provisioning, cloning, snapshotting of virtual machines, all done within vCenter. So there's no separate console, no learning curve to do things like snapshots or the storage management. And then for UCS Manager, we have that vCenter plugin. We have those service profiles, and you can do things like update server firmware, manage the hardware completely, and then if you need to do anything from the console of an individual server, you can do that KVM launch of console direct from UCS Manager, or in fact in the UCS Manager vCenter plugin. So it really does give you that single pane of glass. Drink. So what I'm going to do now is turn this over to Jeff, and he's going to talk a little bit more about a subject that we touched on in the previous session, talking about power and power delivery. He's going to talk about something I've been working on for years, but I've always been interested to hear Jeff's opinion on this, single-phase versus three-phase power. Jeff, over to you.
All right. Thank you so much, Tony. All right, so when it comes to power, you've got a lot of times it's an afterthought, right? So you've got a hardware infrastructure, in place, and got to figure out how to power all this stuff. So what type of power do I use? Do I use single phase, three phase? What sort of connections? Does it matter? Some questions like that. So first, let's discuss the difference between single phase and three phase power. So single phase power is essentially you've got one phase, one sine wave, and you've got with that you'll have a neutral line as well as that phase. With three phase power, you've got three phases that are 120 degrees out of phase with each other. So it's primarily used it's more efficient when distributing power over long distances, and you can get much higher voltages. So with a lot of times when you have a long distance to distribute power, you'll have voltage drop. And in order to overcome that, you use a much higher voltage with three-phase power, so that you don't have that voltage drop. How is it distributed? We've got power that's generated at a power plant, comes out of the plant at three-phase power. It's always generated as three-phase power. Somewhere down the line, if you're using single-phase power, really you're just tapping into one or two of the three phases. So it comes out at up to 400,000 volts, and then goes through secondary transformers. That all the transformer's doing is it's changing the voltage, right? So you can either step it down or step it up. In this case, we're stepping down the voltage through a transformer. Essentially you've got coils of wire inside the transformer. Two different coils have different number of windings that are changing the voltage. Then when you get into the actual data center, a lot of times you're at this point you've stepped it down to 480 volt, could be three phase, 415 volt, and that voltage is measured from phase to phase. So with three phases, you've got A, B, and C, and you're essentially measuring from one phase to the next. And there are depends on the country. It's not a standard across the entire world. It depends on what country you're in. You'll have different voltages for three phase and single phase. When it comes to the difference, there's actually a factor of 1.73. So if you're into math and calculations, so you can always figure out the difference between single phase and three phase voltage when it comes to, if you take the three phase voltage divided by 1.73, that's what your single phase voltage would be. So some advantages of using three phase power. When you're looking at a 20 amp single phase circuit with 110 volts, the amount of power you can actually get from that is 1760 VA. So how we're calculating that is you're taking 20 amps times 110 volts times 0.8. So Y times 0.8. So with all circuits in the United States, you've got, due to electrical code, you've got an 80% derated circuit. So you have a 20 amp circuit. The maximum amount of amps you can actually pull through that circuit is 16. Through a 30 amp circuit, the maximum would be 24 amps. So the difference when it comes to power, the amount of power you can get through a three phase and a single phase, then with looking at 30 amps single phase versus 30 amps three phase, it's about 5,000 versus about 8,646. And that difference is the factor of 1.73 that I mentioned earlier. Another difference is that three-phase power cables are lighter and easier to use. The reason being, to get the same amount of power, you've got a lower amperage that's needed. So because you have lower amperage, the conductor, the wire size is smaller and they weigh less. I mentioned all power is actually distributed as a three-phase voltage, and your single phase is really just using one or two phases of that three-phase system. This is an example in a graph that shows you the actual power that you can get from single phase compared to three phase, from looking at 30 amps up to 100 amps. So it's always a difference of 1.73 between the two, but obviously as you're getting the higher amperages, you have a much bigger difference. Look at the actual power cables here. So with the three-phase delta, you might have heard the term delta. What that means is that there's no neutral line. So you've got a three-phase delta. Looks like a triangle. You've got three different phases: line 1, line 2, and line 3, as well as a ground or an earth. The difference between, in this example, the difference between each line, so between line 1 and line 2 and line 3, or between line 1 and line 3, it's 208 volts between all of those. Divide 208 by 1.73 and you get 120. That's where your single phase voltage would be if there was a neutral line. All right, so now with actually I'm going to go back real quick. I wanted to mention the plug here. So in this plug, you'll see there's actually, there's 4 conductors and on both of those. So these are three-phase plugs. So that means is you've actually got, each one of those conductors is tied back to one of the phases, and then the other one is to ground. Same with the larger blue connector there. There's four conductors in that one. So with the next slide, we're seeing this is a three-phase Y, and in this example, there's a neutral line. So there's a fifth conductor, and now you can see that this is the nomenclature we're looking at here is an L21-30 plug that has the same form, but you also have got in the middle, you've got the neutral line. The way that's represented, the drawing there, now you've got the neutral line, so you can measure voltage between all three phases, as well as the neutral that gets you the 120 volts. Nice thing about the L2130, when you have the neutral present, you have the ability to distribute when it comes to PDUs and power distribution in your rack. It gives you the ability to distribute both 120 and 208 through the same PDU. So you get single phase and three phase right on the same power strip. So always nice to have. Most equipment these days can run at both, but I know predominantly people will run at 208 given the chance because of the differences in efficiency that we'll touch on here in a moment. But it's pretty common you've got stuff that runs off of 120 as well, so it's nice to have that. All right, now some of the pretty standard connectors that you'll see. We've got a 3-pin, which is going to be a single phase, similar to the NEMA version, which is the L6-30, the 30 amp, L1530 that we looked at with the 4-pin 3-phase. And then on the bottom, we've got the 5-pin, so you've got 3 phases, neutral and ground, and then the California style plug there on the bottom right. All right. When it comes to the two single phase and 3-phase, what is the difference between efficiencies here and the voltages? So power supplies operate more efficiently at high voltages, and you can actually see here on the graph the difference between 120 volts in blue versus the 208 volts there in the middle in green, and then at 240 volts on the top in red. You've got the actual efficiency of the power supply depending on how heavily it's loaded. So most of the time, you're going to be running about 50 to 60% load, and you can see there's about a 2% difference across the board. And similar gains are there for your cooling as well. So when you're looking at running cooling at single phase 120 versus a 208 volt, you've also got similar efficiency gains. So what that looks like in an actual energy efficiency. So that of course, what does that actually translate to in dollars? So how does that calculation work? What we're looking at here is the actual cost savings. So I used it shows a larger installation. So if you had, say, 60 servers in a data center, then each server consumes about 1,000 watts. Those are the numbers that I chose to start with, and the calculation for figuring out how much your cost savings are. You're actually charged by the kilowatt hour. So just to keep the math simple, I chose 1,000 watts, so that would be 1 kilowatt over the number of hours per year times. I think I chose 11 cents per kilowatt hour, and about 2% would be times 0.02. It comes out to about $20 per server per year. And then over the lifetime of your server, such as a lifetime of 15 years, you've got the savings there for the actual energy efficiency savings for the power as well as for the cooling. All right, and that's all I had. So thank you guys. Turn it back over.
All right, fantastic. Let's go ahead and answer some questions. We've got quite a few questions here from our audience, but audience members, remember, if you have a question, go ahead and get it in now, and we'll either answer it live or we will take it offline. So let's see. Our first question is from Brandon. He wants to know, can the cost of an expensive UPS outweigh or justify the cost of a potential downtime? Example, migrating to 2003 servers over the weekend when downtime has less impact.
Yeah, I would say it definitely can. It really just depends on how on the downtime, how much money is downtime costing you. But I would say if you look at the cost of an actual UPS versus the potential downtime, I would say it definitely does. And I can follow up with some documentation as well that I've come across in the past, but that's my I would definitely say yes.
Great. Let's see. Next question is from Brian. He wants to know if your DFS is built on an existing DFS or is it completely custom?
So the answer to that is it was built from the ground up by the team at SpringPath. I think, as I mentioned in the presentation, the concept behind log-structured file systems is well known in the computer science environment. If you want, I think out on YouTube there's lectures by computer science professors on what a log-structured file system is and how they work and the full details behind them. So their basic technology is very well known, but the actual development of this log-structured file system, I believe, was done from the ground up by SpringPath.
Great. So I have a question. When you were talking through the plug styles, you mentioned one of them was called the California style. Why is it called California style?
That's a good question.
It's a really good question. I believe it was because it was originally approved in California. I know that, again, this is hearsay. I'd actually have to go look it up in various places. I believe it was originally developed by Hubble, which is an electrical supply company. They do plugs and big power connectors and all sorts of wonderful stuff. And I think may have been originally developed in conjunction with some kind of Californian Standards Authority, but that is somewhat of a guess.
I'm
going to have to look this up now.
Sure, yeah.
All right, great. Thanks, guys. Let's see. Tim has a question. Is this VM agnostic? For example, will it work on a Microsoft hypervisor, VMware, and Zen?
Yes, it will. We haven't done, and SpringPath haven't done the work yet to bring that file system across to those particular hypervisors. So currently, the HyperFlex system only supports VMware, but in future releases there will be support for Hyper-V, KVM, and some of the those kinds of hypervisors.
All right, great. Kyle wants to know, how does Flash have better endurance and better disk performance on the Cisco HX?
So that's to do with the way that Flash actually works down at a very raw level. One of the problems with Flash is it has a limited endurance, where if you do multiple writes to the same block, you can actually wear out that block. And the reason is you can't just rewrite in place in Flash. When you actually write to a block in Flash, what you have to do first is, okay, the first time you write to it, you can just write to it. But every time after that you write to the same block, you actually have to erase that entire block first. So if you're doing a lot of random writes and you're always hitting the same locations, then what you're going to end up doing is wearing out that block of Flash, which reduces the endurance of that Flash. And that's the way typical file systems work, because typical file systems were not designed around Flash. Typical file systems were designed around spinning media, and with spinning media, I can keep writing to the same sector endlessly. It really doesn't make any difference to the lifetime of that sector. What you do with a log-structured file system is it's almost like writing a single big file continuously. You group up the writes into a relatively large block, and then you append to the end of the file. And then as you get new data, you're constantly appending to the end of that file. It's a lot more complicated than that, because obviously you have to go back and mark bits of the old data as not valid anymore. But you're not constantly rewriting the same block, which means that helps to increase the endurance of Flash. And as I said, if you really want to get into log-structured file systems and how they work, there's a couple of presentations on YouTube from computer science professors who go into detail about how log-structured file systems work. But it's sort of inherent in the architecture of a log-structured file system. It happens to map to the way Flash works really nicely.
All right, great, guys. So we are out of questions at this time, but hoping that y'all can tell me a bit more about how our audience members can go about finding out more, learning more about these products, these services, things like that.
And I did want to, real quick, this is Jeff again. I wanted to follow up with Brandon. I found in my documentation here that our marketing team actually did a study for outages and how long they last and how much it costs you. So this was done for small businesses that were defined as less than 100 employees. The average, occurrences per year was found to be 1.7, and for each occurrence, each event, the average length was 2.2 hours. And the average cost per hour was $6,900. So you multiply all that out, and you get about almost $26,000 per year is what they're saying. So hope that answers your question.
All right, fantastic, guys. Thanks for getting to all of those questions. Does anybody have any final words for our audience? All right, fantastic. I do want to remind everyone that if your question wasn't addressed, somebody will be able to follow up with you. And if you had to step out or miss any part of this presentation, you will be receiving an email in just a few days with a link to view the webinar on demand. I want to say special thanks to Cisco and Eaton for creating today's content and sponsoring this great event. And thanks to each and every one of you for tuning in today. We hope to see you back soon for another SpiceWorks Partner webinar. Until then, stay safe and keep it spicy.